Ladies and gentlemen, it is an honor to stand before you today and discuss one of the most profound scientific discoveries in history, Albert Einstein's theory of relativity. This theory, formulated in the early 20th century, revolutionized our understanding of space, time, and the very fabric of the universe. Before Albert Einstein's groundbreaking work, the prevailing view of the universe was based on two separate dimensions: space, which was thought to be a vast, unchanging stage where events occurred, and time, which was considered an independent flow of moments. In this traditional view, space and time operated in parallel but separate from one another. However, Einstein challenged this long-standing belief by introducing a revolutionary idea: that space and time are not distinct entities, but rather a unified, interwoven framework. This notion is central to his theory of relativity. In Einstein's model, the universe is not just a static stage upon which events unfold, but a dynamic, living entity where the three dimensions of space, length, width, and height, are inseparable from the dimension of time. Together, these form what we now call SpaceTime. The significance of this idea lies in how it changes the way we think about how objects and events interact with each other. Rather than considering the universe as a collection of isolated points in space and separate moments in time, Einstein showed that space and time are inextricably linked, and that both can be altered by the presence of mass and energy. One of the key implications of space-time is that what we perceive as a distance between two objects in space can also be affected by time. For example, two events that occur at the same location in space but at different moments in time can be thought of as part of the same event in space-time. This interconnectedness means that the shape and behavior of space-time itself can be influenced by factors such as gravity and velocity, which in turn affects how objects move through space and time. Thus, space-time is not a rigid backdrop against which events unfold. It is fluid, capable of bending and stretching, influenced by the mass and energy within it. This interwoven structure of space and time also leads to mind-bending phenomena, like the warping of space-time near massive objects, such as stars or planets. In the vicinity of these massive bodies, space-time bends in such a way that the paths of objects, including light, are altered. This insight helps explain the strange behavior of objects in extreme conditions, such as black holes, or the bending of light around stars, often referred to as gravitational lensing. Through the concept of space-time, Einstein gave us a new way of seeing the universe, not as a collection of static, separate dimensions, but as a unified whole where space and time are deeply connected. This idea would go on to reshape physics and open up new avenues of exploration in both the small-scale realm of particles and the vastness of the cosmos. One of the most revolutionary aspects of Einstein's theory of relativity is his assertion that the speed of light is constant, regardless of the motion of the observer or the light source. This idea defied centuries of classical thinking and upended our understanding of how motion and velocity work in the universe. And before Einstein, scientists believed that the speed of light might vary depending on the observer's movement, similar to how sound waves change speed depending on whether you are moving toward or away from the source of sound. However, Einstein's postulate introduced an entirely new perspective. He argued that no matter how fast you are moving or in which direction, light will always travel at the same speed, approximately 2.99792 kilometers per second, or about 1.8628 miles per second, in a vacuum. This principle holds true whether you are stationary, moving toward the light source, or moving away from it. This insight has far-reaching consequences. In our everyday experiences, when we move toward something, we approach it faster. When we move away from it, we do so more slowly. If you were driving toward a car with headlights on, you would think you were approaching the light source faster than the light would travel if you were standing still. However, Einstein's theory tells us that this does not apply to light. Whether you are moving toward the source of light or away from it, the speed at which light travels remains unchanged. This realization also had profound implications for our understanding of time and space. If the speed of light were not constant, it would imply that time and space could behave inconsistently depending on the observer's relative motion. For example, different observers might experience different travel times for light to reach them, depending on their own motion. But the constant speed of light eliminates such paradoxes and provides a consistent framework for understanding the behavior of light and the passage of time, no matter where or how you are observing it. This principle also introduced the idea that the speed of light serves as a universal speed limit. Nothing, not even information or matter, can travel faster than light. As a result, light's unchanging speed has become a fundamental constant in all equations of physics, providing a stable foundation for much of modern science. The notion that light cannot exceed its set speed has been confirmed through countless experiments and observations, and it continues to be a cornerstone of our understanding of the universe. Moreover, this constancy of light speed ties directly into other aspects of relativity, such as the nature of time dilation and length contraction. Since the speed of light is always the same for all observers, any changes in the motion of objects must manifest in other ways, such as time running slower for objects moving at high speeds, or distances appearing contracted for fast-moving observers. In essence, Einstein's assertion that the speed of light is constant not only reshaped the way we understand light itself, but also laid the groundwork for the entire framework of relativity. It forces us to rethink the nature of reality and challenges our fundamental intuitions about how the world operates, leading to a far deeper and more interconnected understanding of the universe. One of the most fascinating and counterintuitive aspects of Einstein's theory of relativity is the concept of time dilation, which suggests that time does not pass at the same rate for everyone. It's not a universal, unchanging measure. Rather, it can stretch or compress depending on how fast an object is moving or how strong a gravitational field it is in. Time dilation challenges our common sense and deeply alters the way we understand the flow of time. The idea of time dilation comes from Einstein's special theory of relativity, which shows that as an object moves closer to the speed of light, time for that object begins to slow down relative to an observer who is stationary. This might sound like science fiction, but it is a real, experimentally proven phenomenon. The faster an object travels, the more pronounced the effect becomes. For example, imagine a spaceship traveling at a significant fraction of the speed of light. To an observer who is stationary on Earth, time inside the spaceship would appear to pass more slowly compared to time on Earth. A clock on the spaceship would tick slower than a clock on Earth. This means that, from the perspective of an astronaut aboard the ship, their journey might seem normal, with time passing as it always does for them. But for someone observing from Earth, the astronaut's clock would seem to run much slower. The faster the spaceship moves, the greater the time dilation effect. This phenomenon was first confirmed experimentally with fast-moving particles called muons. Muons are unstable particles that decay very quickly, but when scientists accelerated them to speeds close to the speed of light in particle accelerators, they were able to travel much farther before decaying than they would at rest. This extended lifespan was consistent with the predictions of time dilation, proving that time for the muons slowed down relative to a stationary observer. A thought experiment that illustrates time dilation involves identical twins. One stays on Earth while the other embarks on a space journey at near light speed. When the traveling twin returns after a long journey, they would be much younger than their twin who remained on Earth. This happens because while the traveling twin experiences time more slowly during their high-speed journey, time for the stationary twin on Earth continues at its normal pace. The result is that the traveling twin ages less, having experienced less time passing. The practical implications of time dilation are not limited to hypothetical experiments or space travel. For instance, GPS satellites orbiting Earth must account for time dilation in order to provide accurate location data. These satellites move quickly in orbit, and their clocks run slightly slower compared to those on Earth, but they also experience less gravity, which affects time in a different way. Engineers must adjust for both effects, special relativity, speed, and general relativity, gravity, to ensure GPS systems provide accurate readings. Time dilation also suggests that the flow of time is not absolute, but is relative to the observer's motion. This means that time can appear to speed up or slow down depending on how fast someone or something is moving. It emphasizes the malleability of time, which is something we don't experience in our everyday lives, but becomes incredibly significant at high speeds or in extreme environments like black holes or close to the speed of light. Ultimately, time dilation is a reflection of the interconnected nature of space and time in Einstein's theory. The faster you move through space, the more you slow down your passage through time, revealing that time is not a constant, linear experience. Instead, it is a flexible and dynamic dimension that can bend and stretch, depending on your speed and gravitational environment. In a broader sense, time dilation exemplifies how relativity fundamentally alters our perception of the universe. It challenges the very nature of time as we experience it daily, introducing a complex relativistic view where time itself can bend, stretch, and compress based on the circumstances. This insight not only deepens our understanding of the universe's mechanics, but also opens up new realms of exploration for physicists and astronauts alike. At the heart of Einstein's theory of relativity lies one of the most famous equations in physics, E equals mc2. This deceptively simple formula represents the profound and revolutionary idea that mass and energy are not separate, independent concepts, but are, in fact, two forms of the same thing. The equation shows that mass can be converted into energy, and energy can be converted into mass. The formula consists of three parts. E represents energy, m represents mass. C2 is the square of the speed of light, a constant, approximately 299,792 kilometers per second, or 186,282 miles per second. The speed of light, c, plays a crucial role in this equation, as it acts as the conversion factor between mass and energy. The enormous value of c2 means that even a small amount of mass can be converted into a huge amount of energy. This idea fundamentally changes our understanding of mass and energy, as they were previously thought to be separate, with mass being matter and energy being force or work. Einstein's insight revealed that they are intimately related. The concept of mass-energy equivalence has deep implications. One of the key insights from E equals mc2 is that mass is a concentrated form of energy. This means that all objects, no matter how large or small, have an inherent energy based on their mass. The greater the mass of an object, the greater the amount of energy it contains. For instance, a small amount of matter, like a grain of sand, actually contains an enormous amount of energy, even though it doesn't release that energy under normal circumstances. One of the most important applications of this principle is in the realm of nuclear reactions. In both nuclear fission, splitting atoms, and nuclear fusion, combining atoms, mass is converted into energy. In the case of nuclear fission, as seen in nuclear power plants or atomic bombs, the splitting of heavy atomic nuclei, such as uranium, results in the release of an immense amount of energy, far greater than could be released from conventional chemical reactions. Similarly, in the process of nuclear fusion, like what occurs in the sun, two light atomic nuclei, typically hydrogen, fuse together to form a heavier nucleus, releasing energy in the process. For example, in the sun, hydrogen atoms fuse together to form helium, and in doing so, a tiny fraction of the mass of the hydrogen atoms is converted into energy. This energy radiates outward in the form of light and heat, powering the sun and providing the energy necessary for life on Earth. Without the process of mass energy conversion, stars wouldn't burn, and the energy that fuels our planet wouldn't exist. Another practical application of mass energy equivalence is seen in positron emission tomography, PET scans, a medical imaging technique. In PET scans, particles called positrons are annihilated when they encounter their counterparts, electrons, resulting in the release of energy in the form of gamma rays. This process is directly related to E=mc2, as the mass of the electron and positron is converted into energy. While E=mc2 suggests that mass and energy can be converted into each other, it doesn't mean that mass is constantly being converted into energy in our everyday experiences. However, it does help us understand why some processes, such as nuclear reactions, produce far more energy than we might expect based solely on the amount of material involved. It also provides the foundation for understanding the energy dynamics of black holes, the Big Bang, and the ultimate fate of the universe. In a broader sense, Einstein's equation helps scientists understand the fundamental relationship between matter and energy in a way that had never been conceived before. It challenged old assumptions and provided the theoretical framework for much of modern physics, from nuclear energy to cosmology. The realization that mass can be transformed into energy has far-reaching consequences in both theoretical physics and practical applications, shaping everything from atomic energy to the search for the origins of the universe. In conclusion, E=mc2 represents more than just a mathematical relationship. It encapsulates a profound shift in how we think about the universe. Mass is not just an inert quantity of matter, but a form of energy waiting to be unlocked. This relationship between mass and energy underpins many of the most exciting discoveries in science, from the harnessing of nuclear power to the understanding of the universe's creation and evolution. The idea that mass can be transformed into energy, and vice versa, forever changed the course of physics, offering a deeper and more unified understanding of the forces that govern the cosmos. One of the most astonishing consequences of Einstein's general theory of relativity is gravitational time dilation, a phenomenon in which time passes at different rates depending on the strength of the gravitational field an observer is in. In simple terms, the stronger the gravitational field, i.e., the closer you are to a massive object, the slower time flows relative to an observer in a weaker gravitational field. This is a direct result of the way gravity affects the fabric of space-time. Before Einstein, the concept of time was considered absolute and independent of the physical environment. Time was thought to tick the same for everyone, everywhere. However, general relativity shattered this notion by showing that gravity doesn't just influence objects' motions, it also directly affects the passage of time itself. This means that time isn't a constant, universally experienced flow. Instead, it bends and stretches depending on the curvature of space-time, which is determined by the mass and energy present in a given region of the universe. The deeper you are in a gravitational well, meaning the closer you are to a massive object like a planet, star, or black hole, the slower time will pass relative to an observer further away from that massive object, where gravity is weaker. Essentially, in regions of stronger gravitational fields, time is stretched or dilated. On the other hand, in regions where gravity is weaker, time moves at a faster rate. One of the most famous examples of gravitational time dilation can be seen with black holes. A black hole has an extremely strong gravitational field, especially near its event horizon, the boundary beyond which nothing, not even light, can escape. As an object or even light approaches the event horizon, time appears to slow down from the perspective of a distant observer. For someone near the event horizon, time would seem to pass normally for them, but to an outside observer, it would appear as though time for the object has nearly stopped. This phenomenon has been described as time freezing at the event horizon, although it's important to note that the person or object near the black hole would not perceive this slowing down themselves. In a more familiar context, gravitational time dilation has been measured on Earth and in orbit. For example, clocks on GPS satellites experience time differently than clocks on the surface of the Earth due to the difference in gravity. The satellites are farther from the Earth's gravitational field, where gravity is weaker, so their clocks run slightly faster than those on the Earth's surface, where gravity is stronger. This effect is actually taken into account in the operation of GPS systems. If it weren't for the adjustment of these time differences, GPS measurements would quickly become inaccurate. The mathematical description of gravitational time dilation involves the curvature of space-time, which becomes more pronounced as the gravitational influence of an object increases. The stronger the gravitational field, the more space-time is curved and the greater the dilation of time. This is expressed in the formula for time dilation, where time experienced by an observer near a massive object is related to time experienced by an observer far away from the object. The relationship shows that time near the gravitational source ticks slower when compared to time in the absence of such a source. In more extreme cases, such as near a neutron star or a supermassive black hole, the effects of gravitational time dilation become even more extreme. For example, the intense gravity around a black hole warps space-time to such a degree that time effectively stands still at the event horizon from the perspective of an outside observer. If you were to fall into a black hole, you would experience the passage of time normally. However, an external observer would perceive your time to slow down dramatically as you approached the event horizon, and eventually it would seem as though you never crossed it at all. From your perspective, however, you would continue to experience time as usual. In more everyday situations, gravitational time dilation has been confirmed in experiments involving high-altitude clocks or aircraft traveling at high speeds, where time moves slightly faster or slower depending on the relative altitude and speed. However, these effects are so small that they are imperceptible to humans in daily life. The primary reason gravitational time dilation is so subtle on Earth is because our planet's gravitational field is not strong enough to cause noticeable differences in time passage, except in very precise measurements, such as with atomic clocks. In summary, gravitational time dilation fundamentally alters our perception of time. It shows us that time is not an absolute, fixed quantity, but is influenced by the presence of mass and gravity. The closer you are to a massive object, the slower time flows, and this has real-world applications in technology like GPS and satellite systems. Moreover, in extreme environments like near black holes, time dilation becomes so pronounced that it forces us to reconsider the very nature of time itself, making it a malleable, flexible concept. intricately tied to the structure of space-time. One of the most profound implications of Einstein's theory of general relativity is the understanding that the universe is not static and unchanging, as was once widely believed, but instead is expanding. This idea was a groundbreaking shift in how we viewed the cosmos, with far-reaching consequences for the study of cosmology and the evolution of the universe. Before Einstein's theories, most scientists thought the universe was static, unchanging and eternal, with the same number of stars and galaxies existing in a fixed, unmovable space. However, when Einstein formulated his general theory of relativity in the early 20th century, he realized that his equations allowed for the possibility that the universe could either be expanding or contracting. At the time, however, this idea was quite radical and went against the prevailing view of the universe. Einstein himself didn't initially accept this possibility. In fact, to maintain the idea of a static universe, he introduced a cosmological constant into his equations to counteract the force of gravity that would otherwise cause the universe to collapse in on itself. However, when the Belgian astronomer Georges Lemaitre and later Edwin Hubble showed that the universe was in fact expanding, Einstein famously called the cosmological constant his biggest blunder. The evidence for the expanding universe came in the 1920s through Hubble's observations. Edwin Hubble discovered that distant galaxies were moving away from us. And more importantly, the farther away a galaxy was, the faster it was receding. This relationship is now known as Hubble's law. It essentially showed that the universe was not static, but was stretching, with galaxies getting farther apart over time. This was a monumental discovery because it provided direct evidence for the dynamic nature of the universe. The expansion of the universe can be understood in terms of the fabric of space-time itself. According to Einstein's theory, massive objects, like stars and galaxies, warp space-time, creating what we perceive as gravity. On a larger scale, space-time is not a fixed, unchanging backdrop, but is itself malleable and dynamic. The expansion of the universe is essentially the stretching of space-time itself, causing galaxies to move apart. This expansion doesn't mean that galaxies are moving through space in the traditional sense. Rather, the space between galaxies is stretching, causing the galaxies to move farther apart from each other over time. The discovery of the expanding universe had a profound impact on our understanding of the origin and future of the universe. The expansion implies that, in the past, the universe was much smaller, denser, and hotter. This led to the development of the Big Bang theory, which proposes that the universe began as an infinitely small and dense point, and since then, it has been expanding. This theory suggests that the universe began approximately 13.8 billion years ago in a massive explosion of energy and matter, setting the stage for everything that has happened since. The expanding universe also means that, in the distant future, galaxies will continue to move farther apart. Over time, distant galaxies will move beyond the observable universe, meaning that we will no longer be able to see them. This has led to fascinating speculations about the eventual fate of the universe. Several theories have been proposed, including scenarios where the universe continues to expand forever, or where it might eventually stop expanding and contract back in a big crunch. In more recent times, the discovery of dark energy has added another layer of complexity to our understanding of the expanding universe. In the late 1990s, observations of distant supernovae revealed that the expansion of the universe is actually accelerating rather than slowing down as previously expected. This accelerated expansion is attributed to dark energy, a mysterious force that makes up about 68% of the total energy content of the universe. While we still don't fully understand dark energy, its presence is a crucial factor in how the universe continues to evolve. The evidence for the expanding universe is not limited to distant galaxies and supernovae. The cosmic microwave background radiation, CMB, provides another key piece of evidence for the Big Bang and the expansion of the universe. The CMB is a faint glow of radiation that fills the universe and is a remnant of the early universe. Just a few 100,000 years after the Big Bang, the uniformity and characteristics of this radiation support the idea that the universe started as a hot, dense point and has been expanding and cooling ever since. This expansion is not just a theoretical idea. It has been observed through various means over the past century. In addition to the redshift of light from distant galaxies, we now have a detailed understanding of how the universe expanded through the cosmic inflationary period, a brief period of rapid expansion that occurred just after the Big Bang. The discovery of this period was a critical breakthrough in cosmology, helping to explain the uniformity of the universe on large scales. In summary, the concept of the expanding universe, as revealed by Einstein's theory and confirmed through modern observations, changed our understanding of the cosmos. The universe is not a static entity, but is dynamic and evolving, constantly stretching over time. This expansion has had profound implications for the origin of the universe, the nature of space and time, and the eventual fate of everything within the cosmos. From the evidence of galaxies receding from one another to the discovery of dark energy and cosmic inflation, we now know that the universe's expansion is one of the key features that defines its past, present, and future. In conclusion, Einstein's theory of relativity has not only reshaped our understanding of space, time, and gravity, but has also revolutionized the way we see the universe. From the unyielding constancy of the speed of light to the profound effects of time dilation and the realization that mass and energy are intimately connected, Einstein's insights continue to influence the field of physics to this very day. His ideas have illuminated the vastness of the cosmos, revealing that the universe is dynamic, ever-expanding, and deeply interconnected. And they've shown us that time is not an absolute, fixed measure, but a flexible, malleable dimension, and that gravity itself is a warping of the very fabric of space-time. Thanks to Einstein, we now have a deeper understanding of the forces that shape our universe, from the smallest particles to the grandest cosmic phenomena. His theories have not only changed the course of science, but have also had practical applications, influencing technologies such as GPS, nuclear energy, and space exploration. As we continue to explore the frontiers of physics and the mysteries of the cosmos, we are reminded that Einstein's work is not just a relic of the past, but a living, breathing part of the scientific journey. His legacy challenges us to think beyond the limits of our current knowledge, to question the nature of reality itself, and to keep pushing the boundaries of what is possible. Thank you for your attention today, and as we reflect on the vastness of the universe and the wonders of Einstein's work, may we all be inspired to look further, to question deeper, and to never stop exploring the magnificent mystery of existence.